Hello everybody, welcome back. Welcome to ACE Engineering Academy and ACE Online. Students, here we are in the session of ISRO PYQ series students, right? So, the subject is power system for electrical engineering students. In the PYQ previous year questions series of ISRO students, so we are discussing about the power system previous questions. Right students? So just we'll see here some of the questions we'll discuss in the previous year questions. Almost all the questions whatever we are going to discuss are similar to previous GATE or ESC questions. Particularly in power system students, most of the questions are close to GATE or ESC, close to ESC questions we can say. Right students? So we'll see some of the questions here. So this is the first question. In power lines, series capacitors are used to. In power lines, series capacitors are used to. They have given the options to improve the line frequency, the compensate inductive reactance and compensate capacitive reactance and balance harmonics and balance the harmonics. So let me see. So who are on the line? Let me see who are on the line. Students, any answer here? Any answer here? For this question? Very good students, very good response. Kishore Babu, very good. Manisai, Praveen, Satvik, right? In power lines, the series capacitors are used to compensate inductive reactance, compensate capacitive reactance and compensate the harmonics. So we can say here in transmission line, the series capacitors are used to compensate the inductive reactance of the transmission line. So for a transmission line, in series we are having J times of X line, and this X line can be compensated by using the series capacitor minus J times of XC/SC. And some more points I will add for this one. At a time I will add some more points. By adding series capacitor, the purpose of adding series capacitor, the series capacitor increases the stability of the system, right? And also it increases the power flow in the transmission line. It increases power flow, means the series capacitor is called as a power enhancement device. The series capacitor is called as a power enhancement device. If we are having a question like this, to enhance the power flow in the transmission line, which of the following devices can be used? Means you have to answer as series capacitor. To enhance the power, which of the following device can be used means you have to give answer as the series capacitor. And also students, for leading loads or under no load condition, the series capacitor can eliminate Ferranti effect also. Not only shunt inductor students, remember everybody, not only shunt inductor, the series capacitor also can reduce the value of the Ferranti effect under no load condition. Series capacitor reduces Ferranti effect. Right students? So not only series capacitor, shunt inductor also can reduce the Ferranti effect. Best element is shunt inductor, not the series capacitor. Best element is shunt inductor. Not only that one, for lagging loads, the series capacitor can increase the receiving end voltage. The series capacitor can increase the receiving end voltage for lagging loads. Right, students? Not only series capacitor, shunt capacitor also can increase the receiving end voltage. Not only series capacitor, shunt capacitor also can increase the receiving end voltage. Best element is shunt capacitor to increase the receiving end voltage. To increase the receiving end voltage. So not only this one, I am adding one more point here. For lagging loads, increases receiving end voltages. Right. Series capacitor can increase the receiving end voltage. Series capacitor can reduce the receiving end voltage. But it is not best. It is not best. It is best with respect to stability only. It is best with respect to stability only. Right, students? Very good. Very good, Kishore Babu. Fault current also increases. Perfect. Fault current also increases. Perfect. So, we will go for the next question here. We will go for the next question. Try to give me the answer for this question. The voltage stress will be maximum in underground cable at. The voltage stress. Right. Hello, Shantanu. Right. Hello, everybody. The voltage stress will be maximum in an underground cable at the surface of the sheath, the surface of the conductor, the surface of the insulation, and the surface of the armor. Any answer here? Any answers here, students? Any answer here? The voltage stress will be maximum. Very good, Kishore. Very good, Kishore. The voltage stress will be maximum on the surface of the conductor. See here, students. Here we are having, this is the cable conductor. Upon this one we are having the insulation. Students. And upon the insulation we are having the metal sheath. The metal sheath will be grounded. The electric field intensity will be maximum on the surface of the conductor, and it will be minimum on the surface of the sheath. Inside the conductor, the electric field intensity will be 0. Maximum on surface of conductor, minimum on the surface of the sheath, and E is equivalent to 0 inside the conductor. So that, what is the correct answer? On the surface of the conductor. Maximum on the surface of the conductor. Perfect. Right. Perfect, students. Right. Now we will go for next question. The dielectric stress of air at a barometric pressure of 76 centimeter and 25 degrees centigrade. Standard value, students. The standard value of the dielectric stress. What is the standard value of dielectric stress? The electric field intensity is breaking the insulation at particular value to create corona phenomena or to create the lightning phenomena. Right, students? So, the dielectric strength of air, G naught is 30 kilovolts per centimeter, which is peak value. 30 kilovolts per centimeter peak value, which is also is equivalent to 30 divided by root 2 kilovolts per centimeter RMS value. 30 divided by root 2 kilovolts per centimeter RMS value. 30 divided by root 2 is nothing but 21.21 kilovolts per centimeter RMS value. 30 divided by root 2 kilovolts per centimeter, which is 21.21 kilovolts per centimeter. These values are at NTP. NTP means nominal temperature and pressure. The nominal temperature will be 76 centimeter of Hg and barometric Temperature is 25 degrees centigrade. Temperature will be 25 degree centigrade and barometric pressure will be 76. It will be 25 degrees centigrade and it will be 76 centimeter of Hg. At this condition, it is 21.21 kilovolts per centimeter. Kilovolts per centimeter. 21.21 kilovolts per centimeter. Right, it's not kilovolts per meter, Kishore. It will be kilovolts per centimeter. Right. So, Viraya, very good. Viraya, very good. Very good, very good. Perfect. 21.21 kilovolts per centimeter. So, based on the value, it is 21.1 nearly. Nearly. Right. We'll go for the next question. The positive sequence current of a transmission line is. The positive sequence current of a transmission line is. Option A, always 0. Option B, 1/3 of the negative sequence current. Option C, 3 times that of the negative sequence current. Option D, equal to the negative sequence current. Equal to the negative sequence current. It is always 0 or 1/3 of the negative sequence current or 3 times that of the negative sequence current equals that of the negative sequence current. Any answer here? Any answer here? Respond, students. Respond. Any answer here? The positive sequence current. The positive sequence current. Very good, Kishore Babu. Perfect. Praveen, perfect. Perfect, students. So, what is the answer? The positive sequence current is exactly equivalent to the negative sequence current for a transmission line. For a transmission line, positive sequence current and negative sequence current are exactly same. Exactly same. The positive sequence impedance is Zs minus Zm, which is also equivalent to negative sequence impedance. Impedances are same, the currents are also same. The currents are also same. The zero sequence impedance will be Zs plus 2 times of Zm. Zs plus 2 times of Zm. That is the relation between positive, negative and zero sequence impedances. Very good Abdul. Very good Film Express. Very good students. We'll go for the next question now. For the fault at the terminals of synchronous generator, the fault current is maximum for a fault at terminals of the generator, the fault current is maximum for the fault at the terminals of generator, the fault current is maximum for. Viraya, is it B? Is it B? Is it B? For the fault at the terminals of generator, the fault current is maximum for 3-phase fault, option B, 3-phase to ground fault, line to ground fault, line to line fault. Line to line fault. Students, Kishore Babu also giving it is 3-phase to ground fault. Shantanu, very good. Very good Shantanu, students. Just please check it, students. Whenever you are having a generator here and this is the transmission line, here we are having the load. Here we are having the load. Now, we are having two locations here. This is one location, this is one location. At this location, which is the most severe fault, LG fault is the most severe fault. At the end of the transmission line, which is the most severe fault, 3-phase fault is the most severe fault. So, here we can say at the terminals of generator, for a fault at the terminals of generator, at the terminals of generator, LG fault is the most severe fault, right? For a fault at the end of the transmission line, for a fault at the end of the transmission line, 3-phase fault is the most severe fault. 3-phase fault is the most severe fault. 3-phase fault is the most severe fault. Please check it, students. Very good, very good. LG fault, very good, Praveen, very good. Very good one. Right. It's a very simple question, students. Very simple question. These are the ways, very simple questions they are asking, students. Right. So one more question. For differential protection of power transformers. So transformer connection is delta delta. The current transformers will be. For differential protection of power transformer, delta delta connected transformer, the current transformers will be delta delta, star delta, star star and delta star. What will be the answer? What will be the answer? For differential protection of power transformers, for delta delta connected transformers, Arun Kumar, it's option C. It is given star star, very good. Manisai, very good. Viraya, very good. Very good, students. See here, students, the differential protection needs 180-degree phase angle difference. 180-degree phase angle difference. To have 180-degree phase angle difference. Right, students? Whenever primary and secondary of transformers are there, this is CT1 and this will be CT2. CT1 primary side CT, CT2 secondary side CT. Whenever star star connection of transformer is there, CT1 and CT2 are delta delta. Whenever delta delta connected transformer is there, CT1 and CT2 are star star connected. Whenever star delta connection is there, here we are having delta star connection. Whenever delta star connection is there, here we are having star delta. Right, students? Like that we can give the connection to have 180-degree phase angle difference in case of the differential protection. That's why for delta delta transformer we are having star star connection. Got it right, students? That's about the differential protection. So differential protection is also called as merge price protection. That's extra point you can take. And one more point, it is a unit protective system. And the differential protection applications. What are the differential protection applications? We can use that one for protection of alternators, for protection of transformers, for protection of bus bars also. Right, students? Right. Now we'll see the next question here. This is the next question, students. For the protection of very long extra high voltage line, the protective relay used is. For protection of very long extra high voltage line, the protective relay used is overcurrent with extremely inverse characteristics, percentage differential relay, reactance type of distance relay, mode type of distance relay. For long line protection, which relay can be used? Very easiest question. Viraya, very good. Perfect answer. Very good, Kishore. For the protection of long transmission line, we are going to use the long transmission line. Remember, students, RIM means reactance relay. I means impedance relay. Right. M means mode relay. SML means short, medium, long. Right. So this is for short transmission lines. This is for medium transmission lines. And this is for long transmission lines. So more relay is used for the long transmission lines, right? So remember students, reactance relay also used for earth fault protection, also used for earth fault protection, earth fault protection, right? More relay also used under power swings, under power swings, right students? Reactance relay, impedance relay, more relay. And if you see the reactance relay, impedance relay, more relay characteristics, if you see here the impedance relay, this is the characteristic of the impedance relay in the Rx plane. Just recalling these points students, this is Rx plane, this is for impedance relay, Z relay, Z relay. For reactance relay students, this is the resistance axis, this is the reactance axis, and this is the operating zone, that is the operating zone. This is for reactance relay, X relay, X relay. In the Rx plane, the more relay characteristics will be a circle passing through the origin, a circle passing through the origin. This is for more relay, that is for more relay. Those are the characteristics of the relays. What is the other name of impedance relay? Impedance relay is also called as voltage restrained, voltage restrained over current relay. Impedance relay is also called as voltage restrained over current relay. Reactance relay is also called as directional restrained, directional restrained over current relay, right? And more relay is also called as voltage restrained, voltage restrained, directional relay, directional relay, voltage restrained directional relay. So names also they will ask the questions students. With respect to the names also they will ask the questions. Please go through the different names, right? More relay is also called as angle impedance relay, angle impedance relay. More relay is also called as the angle impedance relay students, right? So please go through these points, right? Characteristics and the different names, and Z relay and X relay, that is impedance relay and reactance relay, are non-directional relays. These two are non-directional relays, non-directional relays. So which is directional relay means more relay, it's a directional relay. More relay is a directional relay, right? Right. Now we'll go for the next question. Some of the points I want to add, right? Why? Because so within this 1 hour, you are not going to learn a total subject, right? Total subject. Just I want to add some extra points only students, right? Next question. Resistance switching is normally employed in. Resistance switching is normally employed in. What is the answer? Resistance switching is normally employed in all breakers, bulk oil breakers, minimum oil breakers, air blast circuit breakers. Air blast circuit breakers. Resistance switching will be employed in. Any answer students? Resistance switching is normally employed in. Very good, Kishore Babu. Very good, perfect, right? Perfect. Resistance switching is generally employed in the air blast circuit breakers. Air blast circuit breakers, right students? Resistance switching is generally employed in the air blast circuit breakers. Got it right? Why? Because the current chopping phenomena is more severe in case of the air blast circuit breakers. That's why resistance switching is required. Resistance switching is required. We'll go for the next question, students. Very good, Viraya, perfect. Air blast circuit breakers, perfect. Right. Now I'll go for the next question. The distribution system shown in figure is to be protected by overcurrent system of protection. For proper fault discrimination, the directional overcurrent relays will be required at locations. Where we are going to place the directional overcurrent relays? Where we are having the directional overcurrent relays? For fault protection, so we need directional overcurrent relays and non-directional relays. Where we are having the directional overcurrent relays? Any answer here? Any answer? Any answer here? Any answer? Right. Here, students. Very good, Viraya. It is option A, 1 and 4. 1 and 4. 1 and 4 are the directional overcurrent relays. Manish Sai given it is option B. Shantanu given it is option C. Students, remember, at the sources, always we are having non-directional relays. At the sources, always we are having the non-directional relays. So, the relays close to source, are always non-directional relays. And the relays close to load, and which experiences current reversal, are always directional overcurrent relays. Right, students? The relays which experiences current reversal are always directional overcurrent relays. Right. The relays placed close to source, 1 and 4 are non-directional, but they are asking for proper discrimination, fault discrimination, the directional overcurrent relays will be, what are those? Where you are having? At the source, 1 and 4 are non-directional, 2, 3, 5. But out of 2, 3, 2 will have current in this direction also. Why? Because we are having source here, This source can supply current like this, Okay. Means 2 and 3 will have current reversals. For 3, current reversal is possible in this direction, For 2 also, current reversal is possible in this direction, But for 5, here we are having load. Load will never supply current in the reverse direction. Means current always flows one direction only. Means relay 5 is not a directional overcurrent relay. Only 2 and 3 are the directional overcurrent relays. So the correct answer is 2 and 3. Right, students? Option B is the correct answer. The relays placed close to load which experiences current reversal are always the directional overcurrent relays. Similar type of question I will ask you one more one. I will ask you one more question. Try to give me the answer for that question, students. Try to give me answer for that question also about the directional overcurrent relays. One more question I want to ask you. See this one. Similar type of question. Apply the logic whatever I told you. Tell me what are the directional overcurrent relays? What are the directional overcurrent relays? The distribution system indicated below is to be protected with overcurrent protection. Overcurrent protection. Identify the locations where essentially directional overcurrent relays will be required, considering proper fault discrimination. See here, where current reversal is possible, where current reversal is not possible. Based on that one, try to give me the answer, students. Based on that one, try to give me the answer. Response, students. Here we are having breaker 1, breaker 2, 3, 4, 5, 6, 7, right? And some are connected to grids, some are not connected to grids. Manisai, very good response, very faster. Kishore Babu, very good. Shantanu, very good, right? Praveen, very good. So that's the perfect answer, right? Grid can supply the relays placed close to source are non-directional. Breaker 1, breaker 4, breaker 7 are non-directional. Placed close to load, this is the load location. Here 2, 3, 6, 5 are there. For 2, current will flow like this also. For 3, current will flow like this also. For 6, current will flow like this also. For 6. But for 5, current flows only in this direction, no current flows in the reverse direction. So the 2, 3, 6 are the correct answers. 2, 3, 6. 2, 3, 6 are the correct answers. Right, students? Very simple question. Right? Very simple question. Right. We'll go for the next question here. The surge impedance of a 400 kilometers long overhead transmission line is 300 ohms. The surge impedance of a 400 kilometers long overhead transmission line is 300 ohms. For 200 kilometers length of the same transmission line, the surge impedance will be. The surge impedance of a 400 kilometers long overhead transmission line is 300 ohms. For a 200 kilometers length of the same transmission line, the surge impedance will be. What is the answer? Very good. Perfect answer, students. Perfect answer. We can say surge impedance never depends on length of line, right? Impedance formula ZC is equivalent to root of L by C. It never depends on length of the line. For any length, its value is always constant only. Right, students? And the value of ZC is approximately 200 ohms to 500 ohms. 500 ohms for overhead transmission line. And its value is equivalent to 40 ohms to 80 ohms for underground cable. 50 40 ohms to 80 ohms for underground cable. Right students? These are also you can remember. Based on this one also you will be having the questions. Right. One more question. Right. In a power network, 380 kilovolts is recorded at 400 kilovolts bus. 380 kilovolts is recorded at 400 kilovolts bus. A 60 MVAR 400 kilovolts. 60 MVAR 400 kilovolts. Shunt reactor is connected to the bus. What is the reactive power absorbed by the shunt reactor? Any answer here? What is the reactive power absorbed by the shunt reactor? Right. We'll see. See here students. Actually question is, at a bus we are having a reactor. Actual bus voltage is 400 kilovolts. Right? For that 400 kilovolts, the reactive power shunt inductor is how much? 60 MVAR. Right students? Actual voltage of the bus is 400 kilovolts. For that one, the reactive power absorbed by the reactor is 60 MVAR. But in place of 400, it is measuring only 380 kilovolts. Right? Means whenever 400 kilovolts is there, it is absorbing 60 MVAR. Whenever 380 kilovolts is there, what is the reactive power absorbed? What is the reactive power absorbed by the shunt reactor? Right students? What is the reactive power? The reactive power is proportional to V square divided by F. As frequency is constant, we can say that Q is proportional to V square. Means Q2 divided by Q1 is V2 divided by V1 whole square students. Q2 divided by Q1 is V2 divided by V1 whole square. Then what is the value of Q2? The value of Q2 is equivalent to Q1 into V2 divided by V1 whole square. Where Q1 is how much? Q1 is 60 MVAR into V2 is 380 divided by 400 whole square. 60 into 380 divided by 400 whole square. So what is the answer? Manikanta, Rangarao, they have given option C. Option C in the sense, can I go for 66.48? 66.48. Please check the calculation once. Students. It is 60 into 400 divided by 380 divided by 400 whole square. 54.15 na? 54.15. 54.15 students, please check it. You are getting it as 54.15. 54.15 it is. Right students? So whenever voltage decreased, okay Manikanta, it is somewhat delayed, I think so. Right. Okay, I can understand. 54.15. Right students? It's a very simple question. V square divided by F. We'll go for next question students. Very easiest question. and very, very important also. Two buses in a system are maintained at the voltages 1.252 at an angle of 30 degrees and V2 is equivalent to 1.35 at an angle of 25 degrees. Bus 1 and bus 2 are interconnected by a transmission line of impedance 1.3 plus J5 ohms. The power flow direction will be, can you tell me the answer, students? What is the power flow direction? Two buses are connected. Bus 1 voltage is 1.252 at an angle of 30 and bus 2 voltage is 1.35 at an angle of 25. Right. The power flow direction. Option A is given, real power flows from bus 1 to bus 2. Real power flows from bus 2 to bus 1. No real power flow between the buses. Reactive power flows from bus 2 to bus 1. Bus 2 to bus 1. Students, the active power is always proportional to delta 1 minus delta 2. Active power always flows from high delta to low delta. Active power always flows from high delta to low delta, but ensure that network is inductive. Network is inductive. Right? In inductive network, active power always flows from high delta to low delta. Means high voltage phase angle to low voltage phase angle. Reactive power always flows from high voltage magnitude to low voltage magnitude only in inductive network. Only in inductive network. Inductive network. So here it is given that 30 degrees. Here it is given 25 degrees. As bus 1 delta is more than that of the bus 2 delta, active power flows from bus 1 to bus 2. Option A is the perfect answer. Right, very good, Shantanu, Kishore, Sai, Praveen, very good responses, students, very good responses. Right, it's like that only we are having questions, students. Just struck onto the basics, whatever you have studied in the subject. Basics should be very clear. Most of the questions are from basics only. Right. Next, the inductance of a transmission line for a length of 400 kilometers in unsymmetrical configuration. When conductors are in unsymmetrical configuration, A phase, that is R phase inductance is given 30, Y phase inductance given at 20, B phase inductance given it is 25. What will be the inductance of each transmission line after transposing? Before transposition, the inductance are different. Once you transpose the transmission line, what is the equivalent inductance value? Yes, very good. In somewhere reactive power flows from bus 2 to bus 1. 1.35. Yes, D also correct, na? D also correct, right? The power flow in the direction, right? Perfect, students. D is also correct, right? The reactive power flows from 1.35 to 1.25. Perfect. I have not observed that one. Yes, very good. Yes, not some way. Perfect way only. D is also correct. Active power flows from high delta to low delta. Reactive power flows from high voltage to low voltage. The voltage. I think by mistakenly they have given two options. Both are perfect only. Right. In an inductive network, active power flows from high voltage to high delta to low delta. Reactive power flows from high voltage to low voltage. Both are perfect only. Now coming to this question. By mistakenly they have given two. Right. You can challenge those type of questions. We can challenge those type of questions. Right, Kishore? By properly explaining them, we can challenge it. Both are perfect only. We cannot say which is exactly correct one. Both are correct only. Right. Inductance of transmission line for a length of 400 kilometers in unsymmetrical configuration is given 30, 20, 25. What will be the inductance of transmission line after doing transposition? After doing transposition. Manikanta given it is option B. Manikanta given it is option B. Any other answers? It's option D, Kishore. 75, huh? It's option D, 75. Manikanta given it is option B, 20. 20. But students, after doing transposition, the inductance, the equivalent inductance, LA equivalent value, that is LR equivalent value for R phase. LR equivalent value, Ly equivalent value, LB equivalent value is nothing but L average value. We have to calculate the average value, no? We have to calculate average value. What is the average value of inductance? LA plus, that is LR plus Ly plus LB divided by 3. Sum of the quantities divided by the number of quantities. Sum of the quantities divided by the number of quantities, that is the average inductance value. How much it is? 30 plus 20, 50 plus 25, it is 75 divided by 3. How much it will be? 25. Right, students? We are calculating the average inductance after doing the transposition. 25 millihenry. So, the correct answer is how much? Equivalent values after doing the transposition, LR is equivalent to LB is equivalent to 25 millihenry, students. 25 millihenry. Right. So, please remember, after doing the transposition, the equivalent inductance of each conductor is sum of all quantities divided by the number of quantities, LR plus Ly plus LB divided by 3, right, and the value is 25 millihenry, right. So, actually we are having conductors in unsymmetrical configuration. The distance are different now, DAB, DBC and DCA. The distances are different. After doing transposition, distance are like this only. But GMD will be same. The GMD, equivalent GMD, we are going to get as cube root of DAB, DBC, DCA. Cube root of DAB, DBC and DCA. Like that you can calculate the equivalent GMD. You will get this value after calculation of this one. You will get the equivalent GMD value, students. Right. So, now we will go for the next question here. Plant use factor is defined as maximum demand to connected load, maximum demand to connected load, number of units generated divided by plant capacity into number of hours plant is operated, average demand to plant capacity, average load to maximum demand. What will be the answer? The plant use factor. So, very good Kishore, very good. That's a perfect answer. The plant use factor is number of units generated divided by the plant capacity into number of hours the plant is actually operated. Very good. It's option B. See, the difference between plant use factor and plant capacity factor. plant capacity factor is number of units generated divided by plant capacity into total number of hours. Right, students? Irrespective of the plant is operating or not. Suppose total units generated, suppose I am taking in a day. In a day, how many number of hours will be there? Total number of hours will become 24 per day. If you go to the plant use factor, it will be numerator is same, number of units generated divided by plant capacity into number of hours plant is operated. So here, suppose if you are taking this one in a day, then here number of hours may be 24 or may be less than 24 also. Why? Because for some hours plant may be off. So that number of hours you have to consider definitely. Right? They will mention in the load curve. Once you have seen the load curve, right? Suppose if the load curve is like this. If this is the power in megawatt or the time, this is the power in megawatt. For the first 12 hours, the plant is on. For the next 4 hours, the plant is off. Means 12 plus 4, it will be 16. Up to 16, the plant is off. For the next hours, the plant is on up to 24. Suppose if this is the load curve, from 12 to 16, the plant is off. That's why the number of hours here it will become 20. For 4 hours, it is off. That is the difference between capacity factor and the use factor. Got it right, students? Now we'll go for the next question here. Similar type of question what you have seen already. Two identical synchronous missions A and B running at same speed are connected to each other through a inductor. Mission A is supplying an active power to mission B and mission B is supplying reactive power to mission A. Then which among the following is correct? Active power is flowing from mission A to mission B. Reactive power is flowing from mission B to mission A. Then which of the following is correct? That's the question they are asking. Students. Any answer here? Similar type of question already we have discussed. Any answer here? Two identical synchronous missions A and B running at same speed, right? So this is one mission, this is one mission. That is one mission. Here it is VA at an angle of delta A. Here VB at an angle of delta B. They are saying that active power is flowing in this direction and reactive power is flowing in this direction. Active power flows from high delta to low delta. Therefore, delta A is greater than that of delta B. But information is not about deltas, it is about voltage. Reactive power is flowing in this direction. Therefore, VB is greater than that of VA or VA is less than that of VB. Right, students? It's a very simple question. Option B. See, recent year questions only they are asking in that area. Very, very important concept, the basic part. Right. Very good, students. Very good response. About the stability, in the stability part. A 90 megawatt 11 kilovolts generator has an inertia constant of H is equivalent to 3 seconds. an inertia constant h is equivalent to 3 seconds. The stored energy in the rotor at the synchronous speed is. What is the stored energy in the rotor at the synchronous speed? They have given the options: 30 kilojoules, 270 kilojoules, 270 megajoules, 30 megajoules. 30 megajoules. Right, students? They are asking what is the stored kinetic energy. Stored kinetic energy. Very good, Kishore. Perfect answer. Kishore, perfect answer. Remaining students. Remaining students. They are very good. Praveen, perfect. Very good. Very good. That's a perfect answer, right? We know the inertia constant h. We know the inertia constant h. H is equivalent to kinetic energy stored. Kinetic energy stored divided by apparent power rating, where kinetic energy is equivalent to S into H. Where S is given. What is the value of S is given? You can take it is 90. You can take it as 90 MVA. Why? Because power factor is not given. When power factor is not given, we can take that power factor is equivalent to 1. 90 megawatt is equivalent to 90 MVA. 90 MVA. For power factor is equivalent to 1, students. And the value of H is given 3. We can say take it as 270. It is in mega. It will be in megajoules. It will be in megajoules. Right? When cos phi is equivalent to 1. Right? So we can take P is exactly equivalent to S. It is 90 MVA or 90 megawatt. Both are same. When nothing is mentioned. When nothing is mentioned. Right, students? Very good. Very good. 3 into 90 megajoules. 3 into 90 megajoules. Right, students? M into G into H, or whatever the formula you have studied. Right? That is S into H. It is 270 megajoules. Same question. More relays are used for protection of. More relays are used for protection of. Directly I can go for long transmission lines. Long transmission lines. Direct question only. HVDC homopolar links. One question about HVDC also. One question about HVDC also, students. I will take HVDC homopolar links uses. One conductor usually of negative polarity. One conductor usually of positive polarity. Two conductors of positive and negative polarity. Two conductors of negative polarity. Students, here 3 types of HVDC links. One is monopolar. Monopolar. In monopolar, we are having only one conductor. Only one conductor. Only one conductor. This is negative polarity generally to reduce corona. To reduce corona. In case of bipolar. In case of bipolar. Here we are having two conductors. Two conductors. One is positive polarity, one is negative polarity. The name itself it is saying that bipolar, two polarities. And in case of homopolar, here we are having two conductors. Two conductors. Both are of negative polarity. Both are of negative polarity, where the ground is acting as the return path. Where ground is acting as the return path. So two conductors of same polarity, that should be which polarity we can take? Negative polarity to reduce corona. To reduce corona. Negative polarity conductors will have less corona phenomenon, right, compared to that of the positive polarity conductors. So what should be the answer now? They are using two conductors. They are using two conductors of negative polarity. Negative polarity. Right, students? Right. So these are the some of the questions, students. Some of the questions. We have covered little bit of questions, students. But by seeing the overview, of the questions, whatever the classes you have listened, students, those classes notes, go through the notes clearly. you can get maximum number of questions, right? And compared to that of the remaining parts of power system, transmission and distribution part, particularly for ISRO level examination or BARC level examination, for local state government examination, in transmission and distribution there will be more number of questions expected, right? And the next level, the next high important part will be power system analysis, right? Later on we will go for the power system protection, and then we will go for the generation of electrical energy also, right students? So these are the questions that we have discussed, right students? So prepare very well students. All the best everybody. So please go with some confidence, right? All the best everybody. Thank you.